Greetings everyone. Today we're going to look at a piece of equipment I haven't covered yet, and it's this combination of transfer relay and attenuator for the IF link, the 144 MHz signal. Our transverter provides a bidirectional receive-transmit link on 144 MHz or IF frequency. This poses a challenge. The challenge is that when we are transmitting, we're sending a minimum of 500 milliwatts into the transverter, and that's way too much, way too much. And then in receive, we want a direct link. We don't want to perform any attenuation. We want to receive the signal and send it into our receiver. So we need some sort of attenuator that will only be applicable in transmit. And in order to do so, we need a transfer relay, a relay that will insert the attenuator when we are in transmit mode. And when we receive, the attenuator is removed from the link and it's a bypass directly to the receiver. And this, of course, would be triggered by an external signal actually coming from the IF radio itself. When we key up the transmitter, it will operate the relay. Of course, there's a sequence that you cannot transmit into the relay until it is completely transferred and the attenuator is back in line. And that's the job of a sequencer, what we call a TR sequencer, and that will be the subject of another video. But for the purpose of this video, of course, we operate this relay when we are in transmit. And for safety reasons, it'll be the other way around. By default, the attenuator will be in line, and it's in the receive mode that we're going to operate the relay here to bypass the attenuator. That's a safer way to work than the other way around. So, of course, I could have bought a transfer relay and then a 30 dB attenuator and the cabling and everything else in between. But that would be definitely more expensive, as I don't have a transfer relay and a 30 dB attenuator. I do have one. But why use off-the-shelf parts if it's easy to create a small box? It will reduce the size a lot. This attenuator, by the way, has to be able to sustain the full power of the IF radio, which is 5 watts, at least for some duration, and long enough to realize that I'm too powerful into the transverter. And of course, that 5 watts attenuated by 30 dB must not harm the transverter. And with the 30 dB attenuator, it will be the case. But of course, the 30 dB attenuator has to be able to sustain 5 watts because I will be operating the rig at 500 milliwatts. So the low one setting, and of course, that will preserve some battery life of my whole system. And I don't need to send 5 watts only to dissipate it into an attenuator. So set it to low level and everything will be all right. Now, let's see the schematic of this box. The solution is based on a regular power relay. It's a Panasonic relay. This DS relay have many of them in stock, so I use what I had. It is discontinued, no longer available new, but I'm pretty sure you can find similar relays if you want to build your own. This is not an RF relay, it's a regular power relay that can take 3 amps. It's not large, you'll see in a couple of minutes. So I use a DS2 Form C, so a double pole, double throw relay. I selected a 5 volt relay, and the reason is I want to put this on the 8 volt receive line to operate the relay. So this is what I show here on the 8 volt receive line through a 1000 picofarad feed-through capacitor. All components here I had. I didn't have to purchase anything. So that's one reason why I wanted to build it, including the enclosure. So how it works? Well, it's a 5 volt relay on an 8 volt link. So I put a 75 ohm voltage dropping resistor, or current drop resistor if you prefer, into the coil. This is not a latching relay. It's a normal relay that transfers over to the normally open positions when the power is applied to the coil, and as soon as you cut off the power, it transfers back. Just a standard relay, really. With a back EMF diode across the coil, I've added an LED to show that the thing is energized on receive. And as far as the RF goes, it's 2 BNCs, input and output. Theoretically, this circuit could be inverted. Either you put the transceiver here or here. Theoretically, it wouldn't matter because electrically it's symmetrical. Now, the thing is, I have one power resistor here, which is not here. So I've dedicated just J1 here as the IF radio port. And like mentioned, by default, this is the resting position of the relay. The attenuator is in line. It's a pi shape attenuator. To design this pi attenuator, you decide how many dBs of attenuation you want. And then there are online websites that will very easily help you create a pi attenuator. So it's really close to 50 ohm, and there's an 820 ohm resistor here, and quarter watt, half watt is enough. The bulk of the power gets absorbed by this 50 ohm resistor here, which takes 99.9% of the power, and then the rest goes through and on to the transverter. And when we are in receive, the relay coil is energized, which swings these two contacts over to the normally open positions. And in that case, we have a direct bypass from the transverter to the transceiver. Now, I've added these protection diodes just in case, for whatever reason, with, for example, the control cable connected from the transceiver to the whole system, if that control cable is disconnected, for whatever reason, if that relay is still energized, that we try to clamp down much of the RF going into the mixer of the transverter. So for protection, I added these two diodes. Frankly, I do not think they're going to survive 5 watts, but I had them, so I decided to throw them in. It's really optional. It's just to absorb some RF power. This have a slight effect on the impedance of that line. These diodes create a capacitance to ground, so it does screw up the impedance a little bit, but not enough to harm us. So that is my transfer relay, and I put it together, and here's how it looks like. So here it is, in a small aluminum box. BNC, one is the transverter side, the other one is the IF radio, so the FT817, and we have a feed-through capacitor for the power, and the relay is activated, of course, when in receive. So we send 8 volts here when in receive, and then when transmit we cut off the supply sent here. I've added an LED also when we're in receive, power receive, the LED will be on. So when looking at the whole system, we can confirm that the different pieces are activated or deactivated. So this is the top side of the box. Now remember, these are 144 megahertz construction techniques. So it's not HF, so short wave, and it's not microwave either, you know. So we can be a bit looser in the rules, but we keep everything very short as possible, and it will work okay at 144 megahertz. So I've used, links, metal links, just a piece of wire connecting to the board. I'll show you the underside in a minute. I have the relay here. It's a regular one. It's a 5-volt relay, so the resistor is right down in here to bring down from 8 volts to 5 volts. And there's a resistor for the LED. But that's pretty much it. I've used a socket. I do not know if in the long term it's going to be a good idea or not, but it's a dip socket and it works well. And I can always remove the socket and solder down the relay if I wish. The relay is pretty much flush with the cover, so it's kept down by the cover, so it's not going to move, not going to come out by itself. Okay, other side. Well, the elephant in the room is the 50 ohm termination. It's supposedly a 60 watt 50 ohm termination, that thing. No way. Even on a good heatsink, I have a lot of doubt. But taking 5 watts by mistake, because I'll be feeding only 500 milliwatts, but taking 5 watts, which is the maximum output that the FT817 can produce, will be no issue. It's heat sunk on the surface. It is grounded. It's not a perfect ground plane. As you can see, each and every hole has its pads on the PCB, but there's a ground grid So between each hole there's the ground strip, so it's really like a grid, a mesh of ground, and this is screwed down against the mesh, and it's good enough, you know, for 5 watts for a few minutes. Remember, 5 watts is not supposed to be the power I'm going to be using. And then a 820 ohm resistor, which is a regular half-watt resistor. And then I use a surface mount, the small one, for the other end of the divider. Now remember, by default, this attenuator is in line. So the relay in normally closed state puts the attenuator in line. This is to protect the front end of the transverter in case everything is shut down and I send in power. Well, it's going to be attenuated, so it's going to be safe for the system. And then for the receive path, when it's in normally open and we activate the relay, it's just a wire between 2 relay contacts, no attenuation. But I did add the 2 diodes to protect. So as you can see, there's some solder. So there was a bit of experimenting here done with the diodes, and that's why it looks a bit messier than it should be. But that's about it. I mean, there's not a lot. I've used also some aluminum tape, self-stick aluminum tape, to bring the ground to the bottom surface as much as possible. And that's pretty much it. As far as results go, we get a standing wave ratio of 1.4 to 1 through the attenuator. I would have liked to have it a little better than that, but it's going to be good enough. And it's about the same when we go in through mode and receive a 1.4 to 1 VSWR, but it's going to be good enough. It's fine, you know, anywhere below 1.5 to 1, I'm a happy camper. So there you go. I'll close the enclosure and install it in my system. All for now. 7-3.